next example is a very famous stopping problem. Okay, it's called the secretary problem. Okay, so I feel like I can't teach a course on stopping problems without doing the secretary problem. Okay, so what is it? Let me get the notes here that I have on it. Oh, let me just check how we're doing for time. You're doing all right for time. Okay. Yeah. So the idea is you basically got to interview people for a job. Okay. You've got to interview N candidates for a position, and it's a secretary's job. It's said in the things, it's a secretary's job. Okay. And the issue with these interviews is that you need to decide at that moment in time, immediately after the interview finishes, whether you're going to hire this person or not. Okay. So someone comes in, you interview them, you go, thank you very much, you've got the job, okay? Or you say, thanks, but no thanks, we're going to interview more candidates, okay? We'll just go through that, through all these N candidates, okay? And the task is to hire the best candidate, okay? So you can imagine that when you interview each person, there's kind of like there is a ranking of the different candidates. You don't know it at the time, okay? So they're all sort of individually, there is a best candidate out there, okay? And when that person turns up, you need to hire that person, okay? So you only get reward if you hire the best candidate, okay? So then the question is, what is an optimal strategy for that problem, okay? So how do you optimally hire the best candidate out of N, okay? Given that you're in this situation where you have to accept or reject offers as soon as they come in, okay? Is that clear with everyone? Okay, I'll just read the text. So we've read the actual text as it says it here. So there are N candidates for a secretary job. You interview the candidates sequentially, and after each interview, you must either accept or reject the candidate. Okay, we assume that each candidate has a rank from 1 to N. Okay. And the candidates arrive uniformly at random, okay? So that just means that they come in an unspecified order. We don't really know from one to the next where they're going to occur in that ranking, okay? So you've just sort of shuffled up the set of CVs and just they've come when they've come, okay? Find the policy that maximizes the probability that you hire the best candidate, okay? Right. Okay, so let's go about answering this question. So you kind of, yeah. This is kind of quite a popular problem. Last time I heard of it, there's this TV program on the BBC called More or Less, okay? And every Valentine's Day, they have like a kind of maths of dating kind of thing. So it's like a kind of statistics program. So they always do the secretary problem. They're always like, okay, so you gotta find the love of your life. And there's only one person. Obviously, once you get married, you're married for life. So you've got, and so this always comes up in this kind of situation. So it's kind of like in popular culture through that kind of situation. Okay. All right. All right. So at the teeth interview, so that's candidate number T. Okay. Know that all that matters is if the candidate is the best so far. Okay? Because if it wasn't the best so far and you hire them, well, you've definitely not got the best candidate. Okay? That makes sense, doesn't it? Okay? So if you want the best candidate and you're at the teeth interview and they're not the best candidate so far. They're certainly not the best candidate overall. Okay, so it's only the state is only interesting if you've got somebody at time t who is the best candidate so far. So I'm going to let the state of the system x of t only be equal to 1 if the person that we've got is the best candidate so far and 0 otherwise. Okay, so indicator function, the current candidate is the best so far. Okay. Okay, and then your actions, okay, are basically either accept or reject the candidate. Okay, so I'm going to say 1 if you accept the candidate and 0 if you don't accept the candidate. Okay. I'm just sort of slowly defining the states of this system, and then eventually we'll write down the Bellman equation and all the rest of it for it. Okay. So I'm going to say 1 if you accept, and 0 if you reject. Okay. Now, a useful little bit of probability is, note that the probability that the teeth candidate is the best overall given that it's the best so far. Okay. Well, let's think about what that is. So if I choose the teeth candidate out of a list, okay, so just choose one of the components here, what's the probability that one's the best? So it's a list of n items, okay? Choose one of the components, what's the probability that's the highest ranked candidate? Good, yeah, okay. And then, if I've got t candidates, okay, so we're doing conditional probabilities here, yeah? So we're doing the probability that the teeth candidate is the best out of all of them, and then I've got to divide that by the probability that the teeth is the best so far. So now I've got t candidates, okay, t numbers, also out of t, which are all given different ranks, with the probability that that teeth one is the best. Yeah, 1 over t. It's the same question. Again, it's t things, you've all got a rank, and you've got them mixed up uniformly at random. Okay? So then, given that, the conditional probability that the nth candidate, teeth candidate, is the best overall, given the teeth candidate's the best so far, is t divided by n. Okay? Okay, and then here, I'm going to let r be our value function. So r of t equal the probability that you select the best candidate given that you've rejected the first t minus 1. Okay? Okay? Okay, and now we need to kind of define the dynamics of the system, okay? So we've kind of got our reward function here. What's the probability you select the best candidate? given you've rejected the first t minus 1. Okay. We've got the states, and we've got some probabilities. Okay. Now we need to be a little bit careful about defining the transitions of this. Okay. So it's kind of one of those problems where I want to write down the Bellman equation straight away, but I kind of need to do some calculations first before I can write down the Bellman equation. Okay. So let's go through the different dynamics. So let's suppose at time t, I've got a candidate and then they're not the best that I've seen so far, okay? Which occurs with probability 1 minus 1 over t, okay? So then I've got two things I can do with this candidate. I can accept them or reject them. Okay, so let's look at the dynamics of what happens. So, if I accept the candidate, what reward do I get? So we've got somebody at time t who's not the best candidate that I've seen so far, and I offer them the job. What reward does that give me? What is my chance of getting the best candidate after that? 0, yeah? So that gives reward of 0. Okay, so you probably don't want to do that, but it's one of the dynamics of the system, yeah? Okay? And you do something more sensible, which is you don't accept that candidate, because they're not the best that you've seen so far. Okay? So what you know is you've seen t candidates, you've rejected all of them so far. Okay? So in the situation where the expected reward going forwards is going to be capital R of t. Plus 1. I should have a plus 1 on there. Okay? I've rejected the first t candidates, and I've got the probability of that I've got to select the best candidate. Okay? All right? Okay. So that's one part. That's from the state where I'm in a state where I've got somebody who isn't the best candidate so far. Now we've got the other case, which is where I've got somebody who is the best candidate so far. That occurs with probability 1 over t. Because like we said, the probability that we get somebody who's the best candidate is 1 over t. Okay. So if I accept the candidate, okay, then I've taken the t candidate in a random list. They've been the best so far, and I've accepted. Okay? So what reward does that give me? What is the probability that that person is the correct candidate? I've already told you the answer. A bit higher up. So basically I've interviewed t candidates, and given that I've been told that that candidate is the best so far, if I accept them, what's the probability that they're the best overall? Yeah, t over n, it's that guy here, yeah? Okay. All right. Or I could reject that candidate, okay, in which case I've just seen n candidates so far, t candidates so far. I don't really know who's going to come next. Could be anyone. All right, so I'm just in the situation where I've interviewed t candidates and rejected them. Okay. All right, so we've sort of got all the all the components that I need to write down the kind of Bellman equation for this guy. Okay? So let's do that. So I'm going to look at the reward at time t, and I'm going to look at what's going to happen based on the candidate that comes in. So remember, in this situation, this is going to slightly change the way the Bellman equation looks. Just note that I see the candidate first, and then I make the decision. Okay? So this is going to be a slightly different form to the way you usually see the Bellman equation, the way we've usually covered it in the course. So normally we have a maximization with an expectation inside. This way we're going to have an expectation outside and a maximization inside. Okay? So let's go through these two cases. Okay? And that's essentially because the random event occurs first, that we see the candidate, and then we do the decision afterwards. Rather than the other way around, where we do the decision and then the random event occurs. Okay? Anyway. So anyway, with probability 1 over t, okay, the candidate's going to be the best candidate that I've seen so far. Okay? So given that they're the best candidate that I've seen so far, I've got two things. I can either offer them the job and I get a reward of t over n, or I can reject them, in which case my expected future reward is rt plus 1. Okay? So I can choose between a reward of t divided by n, or I can keep going, okay, and get a reward of r of t plus 1. Okay? So if you've got these two choices, you're trying to maximize the chance that you get the best candidate, so you choose the biggest of the two. Okay? If it's more likely that they're going to be the best candidate now than me waiting a bit longer, then it's better for me to choose that one. And if this is quite small compared to the expected reward in the future, then it's better for me to reject the candidate and wait a little bit longer. Okay? Okay? Then, let's look at the other situation. With this probability, I'm going to be in this situation where they're not the best candidate I've seen so far. Okay? And you can notice that I either get a reward of 0 for accepting the candidate, or I get the reward rt plus 1. Okay? So then I've got the maximization between 0 and rt plus 1, which, since this is a positive number, it's always going to be rt plus 1 is bigger. So it's always better to accept the candidate. Okay, so that's the Bellman equation. Slightly different to the way you've usually seen it, but it's a Bellman equation nonetheless. Okay? And now I'm just going to kind of, like I say, you kind of write down the Bellman equation, just kind of mess around, okay, and see what happens, okay? So we can kind of simplify this a little bit, okay? And it always depends on the problem how these kind of simplifications go, okay? This is a particularly nice problem where there's a kind of nice form to the solution, okay? So what I'm going to do here is I'm going to notice that I can take the t inside and cancel. So there's a 1 over t and a t here, so I can cancel that, but I also need to divide by t here. Okay? So this is equal to the max of 1 over n, r of t plus 1 over t. And I can also notice that this is just r of t plus 1 here. Okay? Okay. I notice as far as this is concerned, it's just a constant in terms of this maximization. So I can add this to both sides. Okay? So I can basically take this 1 over 1 plus t times RT, and I can add it into here, and I can add it into here. Okay? So let's do that. So we've got the max of 1 over n plus this term here. And I've got this r of t plus 1 over t, and I'm going to add in that term here. And notice I've got a rt plus 1 divided by t and another rt plus 1 divided by t here. Okay? So I'm just going to end up with one lot of r t plus 1. Okay? Now we see a Bellman equation in a slightly more typical form. Okay? That's like the instantaneous cost. That's kind of like the future reward if I continue, and that's the term for stopping. It looks a bit more similar to the forms we've seen previously. Okay? Right. And then we can look at this, and we can decide, essentially, when we've got essentially a term that's a constant plus a linear term in r of t plus a linear term in r of t. Okay? So basically we've got kind of two lines that I have to choose between. Okay? So you can kind of look at when these two are equal to one another, and then that's kind of the threshold for the value of r when it changes from one to the other. Okay? So in particular, I'll let you kind of do the calculations for this at home, but the maximization is given by the r of t term if r of t plus 1 is bigger than t over n. So notice if I solve for this equal to that, when you're kind of indifferent between the two choices, you'll end up with r of t plus 1 equal to t over n. Okay? And when r of t plus 1 is bigger than t over n, you're going to end with this one being the bigger one. And if r of t plus 1 over n is less than t over n, then we end up with this one being the bigger one. Okay? So we'll end up with 1 over n plus t1 minus t rt plus 1 if rt plus 1 is less than t over n. Okay? Okay? All right. One thing you can certainly notice about this is because there's this r of t plus 1 in here and r of t here, that r of t is always increasing. Okay? Because it's always got to be bigger than r of t plus 1. So, I mean, well, decreasing as t goes to infinity. But r of t is bigger than r of t plus 1. Okay? Okay? Which makes sense. You know, you've got more time to make a decision, then you should get a better policy. Okay? Okay? Right. Note. So note here that r of t is bigger than r of t plus 1 from this expression here. Okay? So notice you've got these numbers that are getting sort of smaller and smaller and smaller. Okay? And notice this sort of side of the expression is corresponding to the kind of continue step. And this is, this is corresponding to the continue step, and this corresponds to the stopping step. Okay? So essentially, there's this kind of threshold at t over n, when if r of t plus 1 divided by t gets bigger than 1 over n, okay, then it becomes the point where you should stop. Okay? So somehow this boundary, rt plus 1 divided by t bigger than 1 over n, is kind of the threshold in some way. Okay? So that's kind of the upshot from this Bellman equation. Okay? So we're going to let t star be the biggest t such that r of t plus 1 star okay, is less than t over n. Okay? Or another way to think about this, or smallest t such okay. So essentially, as time gets smaller and smaller, eventually r and t divided by t plus 1 is going to get smaller and smaller and smaller, and eventually it's going to go sort of past this threshold of t divided by n. Okay? So let's start from r of t plus 1, sorry, r star, so r of n plus 1 here. Okay? So that's the state where I've rejected all n candidates. Okay? So what's the reward from rejecting all n candidates? What's the probability I accept the best candidate if I've rejected everybody? It's going to be 0. So I've said rejected everyone, so this has to be 0. Okay? So that's a good starting point. Okay? So from that, I can then get r of n. Okay? So let's suppose we kind of go with the continuation each time rather than stopping. Okay? You can note that so this expression dagger gives that r of t, so notice I'm going to divide by t plus 1 on both sides of this expression. So I'm taking this part of the expression and dividing both sides by t minus 1. Okay. 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 So notice I've got kind of a term here that's the same as this term. All right? The only difference between the t plus 1 term and the t term is 1 over n times 1 over t minus 1. Okay? So I could work out, I'm starting to run out of space a little bit. It's not a problem. I can work out that our t star divided by t star minus 1, okay, is equal to the sum. You've probably seen tricks like this before, just using a nice kind of interpolating series of r of t divided by t minus 1 minus r of t plus 1 divided by t. Okay? Because the last term in here is 0 and all the terms cancel out 1 by 1 if I sum them. Does that make sense? So you've probably seen like things like this all the time in stochastic integration course, where kind of one term, the next, it sort of is called like a diagonal sum or something like this. Okay. Okay. But then I know what the difference is in each of these terms. It's this 1 over n t minus 1. Okay. Okay. So our assumption on, I'll tell you what, I'll get a new page here, I think. New Yeah. If you want to write on the back of the notes, you're very welcome to if you're running out of space as well. Okay. Okay. So in our assumptions on T star, notice T star is the first time such that some t equals 1 to n, 1 over t minus 1, okay, is bigger than 1, okay? Because remember, up here, it's the first time that t star, r of t star gets bigger than t star minus 1 over n, okay? So in other words, this t star minus 1 divided by n has to be bigger than 1 from this term here, okay? So if I substitute in this part into this threshold here, we'll get this expression, okay? All right. Now's kind of the crunch point, and I think your notes are a little bit different. I've got a copy of the notes here. So now that kind of seems a bit confusing, maybe, but essentially the point here is we found a threshold T star, okay, and the policy that it's giving us is saying I'm going to take all of the candidates up to that T star and reject them. I'm just sort of going to explore, check out how people are getting on, okay. It's unlikely anyone that I've seen who's the best so far for that threshold T star is actually the best candidate overall, okay? And then, after that time T star, we want to basically start accepting candidates, and we wait to see who comes along. If they're better than all of the candidates that I've seen so far, then I should accept them, okay? So this gives a policy okay, that you reject sorry, this should be a T star here. Sorry, that's a mistake. You should reject first T star candidates and then accept the next best candidate. Okay, and we can do a little bit better in terms of this. So let's suppose we've got a really big pool of applicants. Okay. So I think this is given us a slightly different exercise. So we're now... Oh yeah, no, it's fine. Okay. So one thing you can notice about this sum, okay, if n is really big, okay, so who's seen sums like this before? So if n is really big, what's that approximately equal to? So sum over 1 over t, from t equals 1 to n. Well, that's approximately equal to the integral from 1 over t dt, yeah? From 1 to n. So this is approximately equal to logarithm of n, okay? So if I had loads and loads and loads and loads of candidates, this is approximately, and gets very close to, log n minus log t star, okay? Okay? We're looking for the first time that this is bigger than 1, okay? So in other words, t star divided by n is approximately, if I rearrange all of this, e to the minus 1. Okay? So that means if you've got a big pool of people that you're trying to recruit for one job and you want to get the best candidate, you basically choose at random e to the minus 1 of those candidates, a proportion e to the minus 1, okay? And then you take the next best candidate after that. So it's kind of one of those weird situations where e crops up for no particular reason, okay? That you take, you know, about a third of the candidates and you just reject them, okay? Okay, a little bit more than a third of the candidate, e to the minus 1 of the candidates. You just interview them, say thanks but no thanks, for no reason at all. And then you just wait, and you use those as sort of evidence, yeah? You're sort of gathering information by interviewing those first 1 over e candidates. And then when you've got sufficient information from that, then you take the next best one, okay? And that's your way of maximizing your chances of getting the best candidates. I don't think we use that for our university admissions process or anything like that, but you know, so it, you know, it gives a sort of important piece of information about how information gathering is very important in decision problems, that you want to kind of accumulate a certain amount of information. We'll cover this more later, okay? And then we want to kind of narrow in on the one that's current candidate that's the best. So that's quite a common feature of different types of decision rules. Okay, so you've well-deserved 10-minute break, I think.